Hello my friend, welcome to TubeU channel. Last week I have made a simple spring scale using a normal extension coil spring. It works very well. In the higher range, say above 100 gram, the error is less than 1 gram using a Vernier Caliper type reader. But in the lower weight range, the error becomes large. Is Hooke's law not suitable for the small range? We will find out the reason now. When you pull the spring scale, the spring extended and they obey Hooke's law. Hooke's law is a law of physics that states that the force F needed to extend or compress a spring by some distance, X scales linearly with respect to that distance. Here is a simple illustration figure that explains the law. When adding a double weight to the spring, the distance of the spring that extended is also twice the single weight value. In mathematics, it is written like this: F equals Kx. Here the weight added is net weight, not gross weight. But in the real conditions, the hanger and hook themselves also have weight. For example, in the case of the spring scale that I made last time, the hanger and hook total weight is 11.1 gram. Let's take a look at the real condition now. This is a spring, and this is the total weight of hanger and hook. We define them as W0. The zero position should be here. The starting position is here. The position is defined as x0. The Hooke's law can be written like this: F is a vector and equals to the mass of weight times gravitational acceleration constant, g. When we add a weight of W, the extended distance x1 and the force can be written according to the equation. If we compare these two equations, we can get this. The additional distance is linearly fitted adding weight. If we add 2 times of the weight, say 2W, the equation can be written like this. So the additional distance for 2W is linearly fitted adding 2W. It looks Hooke's law can fit any range in any case. Now the question is, how can we find the starting zero position? We can use the calibration method and extend the line to the lower range area. It is just what I used last time. But why in the lower weight range it is not fitted the scale bar? Let's see this figure now. Here we already find the zero position. Now weight is hand. In fact, the hanger and the hook weight still exists even it is not so big. In my case, it is 11 gram. If we add a weight, say 100 gram, the extended distance and the weight can be written like this. If we add another weight, say 200 gram, the equation can be written like this. We can see the x2 is a little smaller than 2 times of x1. The adding weight is just 2 times in this case. The reason is that the weight of the hanger and hook is not zero. The smaller weight, the error larger. Here the error is about 10%. For 11 gram initial weight, it is about 1 gram. How to solve this problem? Now the simple way is in the lower weight range. We directly mark the weight and the position line according to the experiments using a digital scale as standard weight. We can see after 100 gram, the scale is almost the same as the larger weight area. Also, we can decrease the hanger and the hook weight. But it always have limitations since we need them strong enough to measure the large weight. Another is to add a compensating unit. In fact, if we check the conventional spring scale, we can see there is a small additional spring. This is worked as a compensating unit. Through these efforts, the simple spring scale can work in high accuracy on a very large weight scale. If you have seen the video here, please do me a favor. Subscribe to my channel and click the small bell, so you will not miss an update. TubeU channel is waiting for you.